Well, hello and welcome back to another episode of Quantitative Bytes. It's great to see you all. I hope you're doing well. So in today's video, I want to continue from where we left off last week, where we were looking at the theory and some of the mathematics behind the gradient descent numerical optimization technique. And today I want to look at the code that I've created to create a practical implementation of this algorithm in C++, which I hope will be of use to at least some of you out there. So as with all of the code that I create, I've really created this to solve my own problems. It seems to work as far as I can tell, and as with any problem of this nature, there are always many different ways that you could go about writing code to solve it. This is simply the solution that I have come up with that is appropriate for what I want to use it for. If you go on to use this code for anything yourself, just be aware, that you should test it thoroughly yourself first to confirm for yourself that it actually does work correctly. I have tested it, and to the best of my knowledge, it does work, but don't just take my word for it. If you're going to use this code for anything substantial yourself, do make sure to test it thoroughly first. Okay, putting that to one side. The previous video, we focused very much on the theory behind gradient descent. If you haven't seen that video already, I strongly suggest you go and look at that first. So I shall put a link up here. I'm never sure which side they come on. And I'll put a link in the description below as well to that. So you can go and watch that video if you haven't done so already, which hopefully gives, I think, a reasonable overview of the theory behind gradient descent. And then, as I say, in this video today, we're going to focus on having a look at a practical implementation of that. So just before we go to the computer and have a look at the code that I've come up with, I just want to say that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. I do try to make a video roughly once a week, so if you subscribe, you don't need to worry about missing anything. Thank you very much. Okay, without much further ado, let's jump to the computer and let's have a look at how we can write code in C++ to implement gradient descent. Okay, so I wanted to recap with quickly looking at some of the content that we looked at in the previous video. I'm not going to go over all of that in any great detail. As I said in the introduction, if you haven't seen that video already, I really suggest you go back and watch that first before watching this one. The focus of this video, as I said, is going to be very much the code, but I just quickly wanted to recap on exactly what the problem is that we're trying to solve. So this is the formula, the equation here for gradient descent that we're working on. So simply, as we said before, we calculate our next location of x, so which is x of n plus 1, from x of n minus some constant gamma multiplied by the gradient of f of x at the location fx of n. So in order to do that, we have to pick a start point, we then compute the gradient at that point, we then calculate the next point, and then we iterate steps 2 and 3, each time taking the new point as being the starting point for the next iteration. And that's what we're going to implement in code, and that's what I want to talk about today. Now, what I've set out to do is to actually create a class to manage this. So I've created a QBGradient class that contains all of the code necessary to solve problems using gradient descent to perform the minimization. And what I've tried to do is to write this in such a way as to be as generic as possible. Now, one thing that I think is really very powerful is that I've done this using function pointers, and these are incredibly useful for this sort of problem. So imagine if we were to create a class for performing gradient descent, if we were just to do that normally, we would probably then have to hard code into that class exactly what the problem is that we wanted to solve, and that's not really very desirable. What we want to be able to do is to be able to create some function outside of the solver class that defines the problem to be solved, and then simply pass a pointer to that function to the solver class so that it can then use that function in order to derive the solution. I think that will become more clear as I go on and explain the code as we go through it. So what I want to start with is simply looking at the header file first, simply because that gives a good idea of how I've structured the code. So we have, of course, initially our include guards. I've talked about those in many previous videos, not going to mention them again. We hash include vector and functional from the standard library. So functional is what gives us the functionality for function pointers. Now, there are other ways of doing function pointers in C++. This is the way I like to do it. I like to use the std : function syntax. I find that very neat and very convenient if you prefer to do it in any other other way, then of course do it the way you prefer. That's quite okay. And of course we bring in vector because we're going to need to store vectors. And then we define our class QBGradient, and we then define our public and private functions and members accordingly. So of course public functions, we have a destructor and a destructor, QBGradient and tilde QBGradient. We'll talk about those. They don't need to do anything very much. We only define a default constructor. We don't have one that accepts any input parameters. We then need our function that allows the user to add a pointer to the object function. So as I mentioned just now, I want this class to operate in such a way that the user can create their own function to be minimized outside of the class and then simply pass a pointer to that function to the class. And they will do that using the setObject function or setObjectFCN function that I've defined here. And this is the syntax here for defining a function parameter that is in fact a function pointer. So we use std : function, and this function will return a double because it's going to return the value of the function at the particular location, and it accepts as input an std : vector of type double, which is a pointer. So a pointer to an std vector of type double. So the input to the function, to the object function as we're calling it, is going to be the current location that we want to evaluate. So that's x of n, or x of n plus 1 in the equations that we've been looking at. And the output, which is just a single value, a single double, is the value of the function at that location. And we write it using the std : vector thing because we don't know how many degrees of freedom or how many dimensions this function is going to contain. So I mentioned in the previous video that one of the powerful features of gradient descent is that it can operate over any number n dimensions. And so we want our QBGradient class to be able to support that functionality. We don't want the user to have to, we don't want it to be hard-coded for a specific number of dimensions. So we keep everything as general as possible. So we're going to represent our location in the function as this std vector of type double, and we don't know how many elements that's going to have. So one of the great things about using the vector class in the standard library is that we don't need to worry about that. It will take care of that for us. If you were doing this in more traditional C or even C++ syntax where you had an array and a number of elements, it would still be possible, but it would be that little bit more cumbersome. Anyway, hopefully the precise functionality of all of this will become more clear later on if it isn't so already. Now we also need a function to set the start point, and we note that this also sets the number of degrees of freedom. So somewhere we need the user to be able to specify how many degrees of freedom there are, but it's a bit redundant to have a specific function for that, because whenever they specify the start point by definition has to have the same number of degrees of freedom or the same number of dimensions as the problem that we're trying to solve. So we simply have a function here called setStartPoint, self-evident, that accepts as input a const std : vector of type double called startPoint. So we are not hard coding how many dimensions there are, but the user then passes a vector into this, and that will specify the start point and also the number of dimensions. We then need a function to set the step size. So this is of course gamma from the previous video, and to set the maximum number of iterations. In case we don't converge to a solution, we want to time out after a certain number of iterations. We don't want it to just loop on forever. We need a function to set the gradient magnitude threshold, which is the stopping condition. Okay, we'll talk about that in a moment. So that's set gradient thresh, and a function to actually perform the optimization, which is simply optimize that we have here, that returns a bool, and then it returns the function location and the function value into these two pointers accordingly. So the way that this will work is that the user will create an instance of the QBGradient class. They will pass to it a pointer, a function pointer to the function to be minimized. They'll set the start point, the step size, the maximum iterations, gradient threshold, and then they'll call the optimize function, and the optimization will be carried out, and the final result will be returned into the these two pointers here. So we have just a number of private functions. We have a function to compute the gradient along a specific dimension. If we look back at the slides momentarily here, we talked about expanding this into any multiple dimensions. And we talked about it, this was in the previous video, we talked about the need to use the partial derivative. So we find for element x1, we find the partial derivative of f of x of n with respect to x1 and so on for x2 down to xm. So we're looking at in each specific dimension individually and calculating the gradient in that dimension as we go. So in code, really what that translates to is we need a function that is going to calculate the gradient in a specific dimension. So we have the function compute gradient, accepts an integer being 0, 1, 2, 3, whatever, corresponding to the number of the dimension that we want to calculate the gradient in, and it returns a double, which is of course the numerical gradient at that of that dimension at that location. And we have a function that compute gradient vector, so that will simply then go through and call compute gradient for each dimension, returning the result in a vector of doubles, which then gives us our overall gradient at a specific location. And then we have a compute gradient magnitude function that simply returns the magnitude of that gradient vector. Okay, really quite simple. If anything about that is unclear, I think it might become more clear as we go on. We then have a number of private variables. We need to store the number of dimensions, we need to store the step size, maximum iterations, we need to store the gradient step size, which we're calling h. That's just a fixed constant. That comes from the equation for finding the numerical gradient, which we can see here. So this is the function that we're using. So h there corresponds to the h in this equation here that we're using to calculate the gradient numerically. Okay, and then we also have the gradient threshold. We need to store the starting point, we need to store our current point of the process, and of course we need to store our function pointer, so the pointer to the object function that we're actually trying to minimize, which is of course std : function, which returns a double and accepts as input a vector of a pointer to a vector of doubles, and we simply call that m object function. So that is actually everything for the header file. It's not too complicated, and hopefully anything that isn't clear now will become clear as we go on. qbgradient.cpp, of course we start by including qbgradient.h. I've brought in iostream and fstream here, which I was using simply for debugging. You don't need those, and math.h that you do need. So obviously we start with our constructor. This simply sets the default values for everything, including h here. We're set to 0.001. That is unalterable at the moment, but for everything that I'm doing, I find that to be okay. The destructor at the moment doesn't do anything, but ultimately that might be necessary to tidy up any memory allocations or anything that we've made. One of the great things about using the vector class from the standard library, of course, is it takes care of that for us, so we don't need to worry about any of those. And we then have our function set object function here, which allows the user to specify the pointer to the function that we want to minimize, and very simply that just does m object function equals object function. So it accepts object function as input and simply stores that into m underscore object fcn like so. So really very simple. We'll see how that's used in a moment, and I think that will make a lot more sense then. We have a function to set the start point, which also sets a number of degrees of freedom. So to set the start point, we simply copy the start point into m underscore start point, and then we simply store m underscore start point dot size into m underscore ndims, and that gives us the number of degrees of freedom, or the number of dimensions of the function we're trying to minimize. We then have the functions to set the step size, set max iterations, to set gradient threshold. Those are very simple. I don't think I really need to talk about those. And then we come to the function that actually performs the optimization. Now this is really the interesting bit, and you can see it's not actually very long. It's only that code. This is the code that actually does the work, and it's really quite simple. Now before we talk about that, I just want to talk about the few private functions that we had. We're going to come back to the function that performs the optimization in a moment. So the first private function we defined is compute gradient, and this computes the gradient of the function along a specific dimension. Now this is where we're actually going to use the function pointer that we've talked so much about. So the first thing that we do is we make a copy of our current location. So m underscore current point, that always stores where we are now in the optimization process. And so first of all, we just make a copy of that into a variable called new point. And then we modify that copy according to the value of h and the specific dimension. Okay, so we take new point at the particular dimension we want, and we add to that m underscore h. Okay, so that is simply doing essentially that in that particular dimension, we're simply taking x plus h, okay, for x1, x2, x3, whatever dim happens to be equal to, and we add h to that. If you find that confusing, I think if you sort of look at the problem on paper, I think that will become quite clear. And then what we need to do is we actually need to calculate the values of the function at these two locations. We now have two locations. We have m current point, and then we have our new point that we've modified in only one dimension, and we want to calculate the function value of both of those. And that's actually really easy to do. We just define two doubles, so double func value 1, and then we're calling whatever the function pointer is at m function pointer. So you remember we defined our function pointer that it returns a double and it accepts as input a pointer to an instance of the vector class from the standard library. So all we have to do is call whatever is pointed to by m underscore object function, and we pass to it a reference to m current point, it's our current point, and that will return a double containing our function value. And this function can be absolutely anything defined by the user outside of the class, as long as it accepts as input an instance of the vector class in the standard library and returns as output a single double value, then that will work. Our actual solver class, the QB gradient class here, does not care or even need to know what goes on inside that object function. All it needs to do is be able to pass to it a location as a vector and retrieve from it a single value of type double, and that is it. As far as this class is concerned, that is everything that we need to know. We then do the same thing for the new point. Okay, we calculate function value 2, and then we'd return the gradient as simply being func value 2 minus func value 1 divided by h. Okay, and that is from this equation here. Very simply, we have fx plus h, that is func value 2 minus func value 1 divided by h. Okay, so fairly basic. Okay, and then we have a function to compute the gradient vector, and all that's going to do is simply loop over all of the dimensions and call the compute gradient function that we've just talked about for each function in turn, and store those values in a vector as we go. So we simply define our vector called gradient vector. Initially we make it equal to m gradient point, just so we get the right size and everything, and then we simply use this syntax here to modify the elements of that to be the gradient, and we return it. Very simple, don't really need to talk about that very much more. And then a function to compute the gradient magnitude. Well, that's very simple. Using Pythagoras, we simply loop over all of the dimensions in our gradient vector, and we define a double. We define a double vector magnitude initially set to 0, and then we loop over all of the dimensions in our gradient vector, and simply do vector magnitude plus equals gradient vector, that dimension multiplied by gradient vector and that dimension, so that's squared, and we add up all of the squares, and then we simply take the square root. Okay, so all very simple. Now let's go back to the actual function that performs the optimization. This is really the interesting bit. This is the bread and butter, if you like, of the code that we're talking about today. So all of this accepts as input simply two pointers to a instance of the vector class in which we're going to store the location of the minimum that we found, and a pointer to a double. So the first thing that we do is we set current point equal to the start point. So the current point is the point we're currently considering, and initially we're going to set that equal to the start point that the user has specified. And then we're going to need to set things up so that we can loop through and perform all of the iterations. If you remember from the previous video, I talked about how this is an iterative process. So we start out by setting iteration count to 0, and we set initially a gradient magnitude here of type double to 1.0, and then we have this while loop here. So we're going to loop continuously while iteration count is less than the maximum number of iterations and the gradient magnitude is greater than our m gradient thresh stopping point. So we will stop when the gradient of our function at that point falls below this particular threshold, or if we reach the maximum number of iterations, whichever one of those comes first. So the first thing we do inside the loop here is we compute the gradient vector. So we have to simply define gradient vector there is equal to compute gradient vector. We call the function we've just talked about to call compute gradient vector, and then we calculate the gradient magnitude, again using the function we've just talked about, compute gradient magnitude. So very simple. And now we calculate our new point. Now, if we look back at the equation that we have for gradient descent, the new point, xn plus 1, is equal to our original point minus gamma multiplied by the gradient of the function at the location x of n. Okay, so this is what we're going to implement now. And that's actually very simple. What we do is we create a vector of type double for our new point, which we set initially equal to m current point, and then we're going to go through and modify. And we simply loop over each of the dimensions, and for each dimension, we take each element of new point, which is simply equal to whatever it was before, plus the negative of the gradient vector for that dimension multiplied by the step size. And that's actually it. That's really all we need to do, and that gives us then a vector that contains our new location called new point. And simply all we need to do is update the current point, so we set m current point equals new point, we increment our iteration counter, and then we loop through and we do that again. I think if you look at that in connection with the slide that I've just shown with this one, this describes the iterative process here, and if you compare that with the code that we have here, I think that should hopefully make sense. It is actually fairly simple to implement this algorithm in code, and it can be immensely powerful, subject to the caveats that I talked about in the previous video, which are, of course, it's important to choose the correct value of gamma, and it is important to choose a sensible starting point for your specific problem. Subject to those caveats, this is actually a very powerful optimization method, which is surprisingly simple to implement in code. So let's now have a look at how we would actually go about testing this. So I've created another file here called main.cpp, and this is going to be the main code that we run in order to test it. So let's just ignore this bit of code for the moment. I'm going to come back and talk about that in a minute. So our main entry point, int main, int argc, char star argv, standard definition, C++ code. The first thing we do is we're going to create a function pointer for our object function. Now, I mentioned before that the class, the QB gradient class that we've created, does not care, or in fact does not need to know anything about what the object function is. The object function only has to conform to the particular standard definition. It has to return a double, and it has to accept as input a vector, an instance of this vector class in the standard library of type doubles, or pointer to that. And we create our object function really very simply. The first thing that we do up here is we actually create initially our object function, which we've called object FCN, and it has the prototype that we've just talked about. It returns a double, and it accepts as input an instance of the vector class in the standard library of type double, which we're calling star funclock, so it's a pointer to an instance of that. Okay, and all it has to do is simply retrieve the value of x from funclock. So we use funclock at 0. So this is at the moment a code written for a one-dimensional example. So initially I'm looking at the problem of f of x equals x squared, because that's the first example that we looked at with our slides in the previous video. So we're looking at that here. And all this object function has to do is accept as input a location here, funclock, right, and it then simply returns x times x, which is of course x squared as a double, and that's it. And the only other line of code here that's active at the moment, all of these other commented out bits of code here are for other examples. The only other line that's active at the moment is this double x equals funclock at 0. So that retrieves the 0th element of funclock and stores that into our variable x, and then we simply return x times x here, and that is actually all that we need. We could delete all of this commented out code, and our object function then consists of only 2 lines of code, and that's it. And now all we have to do is create a function pointer pointing to that, which we do using this syntax here, so std : function, and then we specify the form. So we have as output a double, and we have as input a vector of type double, or pointer, sorry, to an instance of the vector class of type double, and we're going to call it p object function, and we're going to build it out of object function. So see here, object function, that's this function we've defined here, and we'll create our pointer called p underscore object function. And that's it. And this function, we can put anything we like in there. It can be a simple mathematical equation like we're doing here in these examples, or it could be anything. It could be any other code that defines a problem that we want to minimize. And that's really where this approach becomes immensely powerful. Okay, so moving on, we create an instance of our QB gradient class called solver, and then we assign the object function to that. So we just do solver.set object function p underscore object function. So that's the pointer that the function pointer that we've just defined. We simply pass that to the solver using the set object function method. We set our start point, which has to be defined as a vector. It has, in this instance, only one dimension, and we want to start at minus 1.0, like so. Let's just save that. So we then do solver.set start point, easy. We set the maximum number of iterations to 50. We set our step size to 0.2. So I know those are the parameters that work well for f of x equals x squared. And then we simply call our optimized function. So first of all, we define std vector of type double called funclock, and we define a double for our function value called funcval, and then we just do solver.optimize, and we pass a reference to funclock and a reference to funcval, and that will give us the outputs accordingly. And then I've simply put in some code here to output those so that we can see the result. And that is literally everything that we need to implement this technique. Now, in order to show that it works, let's just go to a terminal window. Now, I've created a makefile just to help with compiling this, but you can see what that does, just g++ -o main.o, main.cpp, etc., using C++ standard 17, so C++ 17, that is important. And yeah, so you can see how that compiles. You can compile it any way that you wish. And then we can simply run our code with /main, and we get these values. So we get a function location of minus 0.0005, which is very close to x equals 0, and a function value 2.5 times 10 to the minus 7, which is very close to 0. Now we know that that is actually what the location should be. But if we look at a more complicated example, and we looked at this quartic function, we know that the solution actually occurs around about here. So let's have a look at that with the code. So in order to implement that in the code, we simply need to modify our object function accordingly. So we need to comment out return x times x, which is of course f of x equals x squared, and replace it with this. So here we have x times x times x, which is x to the 4 plus 2x cubed minus 6x squared plus 4x plus 2, which is of course the function that we have here. So if we run our code now, we should return the solution or approximate solution to that equation. We do need to make some minor changes though. We need to change the start point to minus 4, and we need to change the step size to 0.01, like so. So if I go back to my terminal window, I need to compile the code first. Okay, and then if we run it /main, like so, then we get these values of minus 2.73 for the function location, that's the value of x, and the function value there is minus 38.78. Now I've solved those using other software. You can indeed solve them analytically yourself if you wish, and I know that those are actually quite good approximations to the actual value. And if we look back at the slide, we can see 2.78 there, that makes sense, and again minus 38, we're just above minus 40 there, so again that seems perfectly reasonable. And that is actually everything that we need to do. The one last thing to look at would be if we were to do a function of two variables. So I've mentioned, you know, that the QB gradient class doesn't really care how many dimensions we're using. All that we need to do is make some changes to here. If we're using two variables, we need to return x and y for our location. So in our object function in main.cpp, we would put that in. So we retrieve the value of x from the first element of funclock and the value of y from the second element of funclock. And then of course we need a function. So let's look there. We have x squared plus xy plus y squared. That's the function we used in the example, and we'll save that. We need to specify a start point, which now has two values. So we go 5.0, 5.0. Step size 0.01, we can leave that as it is. Okay, so this is the equation that we're solving now, x squared plus xy plus y squared. We'll put gamma as 0.1, not 0.01, apologies. Gamma at 0.1, like so. And that's actually everything that we need to change to solve a function of two dimensions. And you can see, in fact, we could have as many dimensions as we needed. It really doesn't matter. There's nothing else that needs changing. So we simply go back to a terminal window. Well, let's compile our code again and run it. and we get the answer. So we get a function location of minus 0.0003. That's very close to 0. Now we've only plotted, let's actually just change that. So at the moment we're only outputting funclock 0, but of course we now have a two-dimensional function, so we would add funclock 1 to that as well, like so. Okay, so let's do that again. Back to the terminal window, just clear that. Let's compile and run our code, and there we go. So we get x as minus 0.0003 and y of minus 0.0003, so that's close to 0, 0, which we know to be the minimum, and the function value 3.3 times 10 to the minus 7 is very close to 0. So we can see how incredibly easy it is to use this new solver class. We can define any function really that we like here in our object function. It doesn't have to be a mathematical function like this. It could be anything. And indeed, what I want to go on to do in subsequent videos is to actually use this to do image registration, in which case what we're going to put in here will be the code to compare two images together, and then the function that we're minimizing will be a transform applied to one of those images in order to bring them into alignment. But we'll see more of that when it comes. For now, you can probably see for yourself that really we could put any code that we want in here, as long as it returns a double and accepts as input a vector of doubles or pointer to a vector of doubles, then it can be anything. Well, that's everything I wanted to talk about today. We've covered a broad overview of a very simple implementation of the gradient descent algorithm in C++, and we've given some examples and everything, and I've shown how the implementation that I've come up with can be used to solve simple numerical optimization problems. So I really hope you've liked this video. It's been a great deal of pleasure making it. Just want to say, if you have enjoyed it, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Okay, well, I really hope you've enjoyed this video, and I really look forward to seeing you in the next one. Thank you very much for watching. Bye.